Okay, so today we are going to take a look at Newton's laws of motion. We have 3 laws of motion that Newton came up with, but there's actually one that you guys don't know about, which is the law of universal gravitation. So we'll be talking a little bit about that today too. So just as a quick review, we're going to go over Newton's 3 laws that you should have learned at some other point in time in your high school career, but if not, we're going to just kind of review them. So we're going to start with Newton's first law of motion. And you should have this in your warm-up, but it might be worthwhile for you to recopy it down. An object in motion stays at motion, and an object at rest stays at rest until acted on by an outside force. This is also called the law of inertia. Inertia is the concept that everything in the universe is lazy, and it won't move unless it absolutely has to. So that is Newton's first law of motion. Inertia is an object's resistance to change. So the more massive an object is, the more inertia it has. So if you think about it, you could probably slide your chair across the floor pretty easily because it doesn't have much mass, but you probably can't slide a pickup truck or a Mack truck across the floor because it's much more massive. So its inertia is going to increase. So as an example, it's a lot harder to push something heavy than something that is light. So that is Newton's first law of motion. And again, if you need to pause the video, go ahead and pause it right here so you can get everything written down that you need to get written down. Okay, moving on. Newton's second law is the law that we've been working with the most this chapter. It states that acceleration is equal to an object's force divided by its mass, or as we know, an object's force is equal to its mass times acceleration. So there's a proportional relationship between acceleration and mass in order to calculate the force. And Newton's third law: for every action, there's an equal and opposite reaction. There's an action force and a reaction force. So that doesn't mean that if I walk up and punch somebody in the classroom, they punch me back. That's not an action and reaction force. It's basically saying that when you push on a wall, the wall pushes back on you with the same force. It doesn't necessarily mean that the forces will cancel each other out, though. So you do have to be careful with that, and that might be something that shows up on a test in another day or so. I don't know where I maybe heard that, but I'm sure you guys know. So Newton's third law: every action has an equal and opposite reaction, or more friendly language, forces act in pairs. Forces act in pairs. So we're going to take a look at Newton's law of universal gravitation. And when we think about gravity, gravity is kind of a funky thing. We want to know, why does gravity work? Well, science doesn't really know, but objects exert gravity because of their mass. It's as a direct result of their mass. So we have this concept called gravity. We're not real sure why it happens that way. Nobody knows. And if I knew, I think I probably would be making billions and billions of dollars somewhere else. So I don't have the answer for you because nobody really has a good answer for it. But we do know it has something to do with mass. And the interesting thing about gravity is that we can determine just how much gravity something's going to have, or what the force of gravity is going to be, based on or when 2 objects interact with each other. And lots of people will ask, oh, hey, what happens? Do Newton's laws apply in outer space? Well, yes, they do. But if we think about it, there's one aspect that does not apply in outer space, and that's that concept of acceleration due to gravity being negative 9.8 meters per second squared. Because that only works on Earth. On other planets, that little g value, that acceleration due to gravity, is going to be a different number. So for every planet, it's planet or object or moon or whatever, that object is object specific. So is there a number that can capture all objects? And what you guys are about to find out is that there is, and that's called Newton's law of universal gravitation. So Newton's law of universal gravitation, this is kind of a Newton's fourth law, if you will, it says everything pulls on everything else that has a mass and a distance. In other words, if you have a mass and you are a certain distance from something, you do have a gravitational effect on it. So maybe Star Wars wasn't really that far off back in the day. That's not true. You can't really use the force. But this would probably be a concept that maybe they used or went off of in order to create that idea. So there's an equation that goes with this law of gravitation. So just like there's an equation for Newton's second law, there's an equation for Newton's universal law of gravitation. And it's F, that force, that gravitational force, is equal to capital G. If you guys notice here, this is a capital G, not a little g. So this is not 9.8. It's a different number, which we'll get to in a minute. And that's equal to the mass of one object times the mass of the second object divided by the distance squared. So the way that this actually looks, guys, because they didn't put subscripts in here when the PowerPoint came up, is you have F. Of course, this pen doesn't work when I need it to. There we go. We have F is equal to capital G times the mass of the first object, because we're talking about gravity between two objects. So like Earth and the moon, Earth and the sun, etc., etc. So the mass of the first object times the mass of the second object divided by the distance squared. That's how that equation should look. Big G times m1, m2 divided by d squared. Okay? All over d squared, where m1 and m2 are the masses of the two objects in question, d is the distance, f is the force, and g is the universal gravitational constant, the universal gravitational constant. You're like, what is a universal gravitational constant? Well, basically, when Newton was trying to figure out what that relationship was between two masses and how gravity was impacted by that, he kept coming up with a good relationship, and he got this really good relationship between these masses and the squared distance here, but it was always off by a certain number, and it just wasn't working out right. And he found that if he included this constant number every single time, that we would get a true answer for this. And what is that number? Well, that number is 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. So how does that actually look when we write it down? Capital G is equal to 6.67 times 10 to the negative 11th. So that's a tiny number, right, because we have a negative here. And the unit is a Newton meter squared divided by kilograms squared. So that's that funky number. And basically what he was finding is that it was always off, or what he was trying to calculate was always off by this special number. So we call it a constant. It's not really anything that has, it's only got value to help make the equation work. And the reason why the equation can still work is because this number is always the same. So a lot of you guys are like, well, how can't you just add a number in and everything's fine now? Well, yeah, but the number is exactly the same every single time. So it means that there's something to it. So what are the rules involving universal gravitation? Well, distance from the center of the object has a bigger effect on the force of gravity between two objects. And you're going to want to write this down because you might see it on a test soon. So distance from the center of the object. So when we talk about masses, we talk about masses from their center. And usually when we talk about this particular equation, it has to do with planets and moons and things like that, which are all spherical objects. So it's basically from the center of the object. And the further away they are, the less effect they're going to have on gravity. Or the less effect gravity is going to have. Distance is the biggest factor. So the closer you are, the greater gravity you have on something. The further you are away, the less effect you have. It applies to any two masses, and it applies everywhere to any two masses. In other words, yeah, it's a number that, or a concept that's used frequently in stars and planets and things like that, but it actually does apply here on Earth as well. So it applies everywhere. It is always attractive. It's always attractive. In other words, gravity is always going to be an attractive force. Gravity is never going to cause something to push away. So in other words, it always encourages masses to come together rather than to repel one another. And again, this universal gravitational constant is this value for capital G. There's a difference between capital G and little g. 6.67 times 10 to the negative 11th. This isn't something that you're going to have to memorize right this second, but you're eventually going to see it when you go into AP chemistry or IB chemistry, etc., etc. Or not chemistry, physics, my bad. So once you get into your physics classes, you'll need it then. So this is the latest equation that we're going to be working with, and we will be working with this particular equation, and I'm going to teach you a really neat trick that you can apply to anything when using this equation. So it's less about calculating an actual number today and more about seeing what the relationships are between these three numbers here and how it impacts the force. So that's what we're going to be doing today. So grab out your homework packet, not your in-class practice packet, your homework packet, and we're going to do some examples on page 25 of your interactive notebook. I think it's page 25 of your interactive notebook. Let me double check. Yes, 25. Page 25. So you should have been taking notes on page 25, but we're going to do some examples right now with that in just a minute. Okay?